This video gives some definitions and facts related to maximum and minimum values of functions. A function f of x has an absolute maximum at the x value of c if f of c is greater than or equal to f of x for all x in the domain of f. The point with x and y coordinates of c, f of c, is called an absolute maximum point, and the y value f of c is called the absolute maximum value. Now if I draw a graph of f, the y value f of c is the highest value that that function ever achieves. And an absolute maximum point is just a point where it achieves that maximum value. Now it's possible for a function to have more than one absolute maximum point if there happens to be a tie for the highest value, but a function has at most one absolute maximum value. A function f of x has an absolute minimum at x equals c if f of c is less than or equal to f of x for all x in the domain of f. In this case, the point c, f of c, is called an absolute minimum point, and the y value f of c is called the absolute minimum value. In the graph of f of x, f of c is now the lowest point that the function achieves anywhere on its domain, and c, f of c are the coordinates of a point where the function achieves that minimum value. For example, this function has an absolute minimum value of about -8, and it has an absolute minimum point with coordinates 3, -8. If this function stops here and just has a domain from 0 to 4, then the function has an absolute maximum value of 10 at the absolute maximum point with coordinates 4, 10. If, however, the function keeps going in this direction, it will not have an absolute maximum value at all. Absolute maximum and minimum values can also be called global maximum and minimum values. In addition to absolute max and mins, we can talk about local max and mins. So a function f of x has a local maximum at x equals c if f of c is greater than or equal to f of x for all x near c. By near c, we mean there's some open interval around c for which this is true. For our graph of f, we have a local maximum right here. Even though it's not the highest point anywhere around, since there's a higher point up here, this is the highest point in an open interval around c. The point c, f of c, is called a local maximum point, and the y value, f of c, is called a local maximum value. Similarly, a function f of x has a local minimum at x equals c if f of c is less than or equal to f of x for all x near c, and the point c, f of c, is called a local minimum point, and the y value f of c is called a local minimum value. A function might have many local minimum values. In this example, assuming that the domain is 0 to 4, we have a local minimum point right here because it's the lowest point anywhere nearby. It also happens to be an absolute minimum point. Now turning our attention to local maximums, we have a local maximum point right here with coordinates about 1, 2. Since f of 1 is as high or higher than f of x for any x value in an open interval around 1. In this example, the absolute maximum point of 410 does not count as a local maximum point, simply because we can't take an open interval on both sides of 4. The function doesn't exist on the right side. And so for that sort of technical reason, we end up with an absolute maximum point that's not a local maximum point here. Local maximum and minimum values can also be called relative maximum and minimum values. Please take a look at this graph and pause the video for a moment to mark all local maximum and minimum points, as well as all global, that is, absolute max and min points. See if you can find the absolute maximum value and the absolute minimum value for the function. I'm going to mark the local max and min points in green and the absolute max and min points in red. The function definitely has a local min here, since this is the lowest point anywhere nearby in an open interval, and there's a local max point here. There's also a local min point here, where the function also hits a low point in an open interval, but that local min is also an absolute min, so I'll mark it half green, half red. There's also a local min point here at the point 3, 2. Since this point is as low or lower than any point in an open interval, and the function is defined in an open interval around 3, even though it's discontinuous there. In fact, this point is tied for local minimum with all the points on this interval here between 2 and 3. They're all as low or lower than all points in an open interval around them. The point 0, 4 doesn't count as a local max because the function's not defined on the other side of 0. So there's no open interval to consider. This point is also not an absolute maximum because the function gets higher over here. In fact, as long as this trend continues, the function f of x has no absolute maximum value at all because its values just keep getting higher and higher as x goes off to infinity. There's one more point that I want to consider, and that's this point here at 3, 3.5. Well, it's tempting to say that f has a local maximum here. It looks like it's the highest point on the ground, but in fact, there is no point here at 3, 3.5, right? The function's value at 3 is actually down here at 2. So there's no point here to be a local maximum point. And if you start looking at points really close to that point, those aren't local maximums either, because you can always find a point just a little bit higher as you get closer and closer, but don't quite reach this missing point of 3, 3.5. So we have all the absolute and local max and min points marked, and now to find the absolute maximum value, well, we just said that there is none, but the absolute minimum value is the y value of this absolute minimum point here, so I'd say that's about 0.5. Here I've drawn the graph of a function. What do you notice about the derivative of this function at its local maximum and minimum points? Please pause the video and think about it. Well, the local maximum and minimum points are here, here, and here. And at 2 of those points, the derivative, f prime of c, equals 0. And at the third point, f prime of c does not exist because the function has a corner. A number c is called a critical number for a function f if f prime of c does not exist or f prime of c exists and equals 0. So in other words, all of these local maximum minimum points for this example, they're all critical points. And this is true in general. If f has a local max or min at c, then c must be a critical number for f. We also say that the point c, f of c, is a critical point for f. It's important not to read too much into this statement. This statement says that if f has a local max or min at C, then C must be a critical number. But the converse doesn't hold. In other words, if C is a critical number, then f may or may not have a local max or min at C. One example to keep in mind is the function f of x equals x cubed at a value of C of 0. Since f prime of x is 3x squared, we have that f prime of 0 equals 0, so 0 is a critical number. But notice that f does not have a local max or min at x equals 0. In this video, we defined absolute and local maximum and minimums. We also defined critical numbers, which are numbers C where f prime of C equals 0 or f prime of C does not exist. We noted that if f has a local max or min at C, then C is a critical number, but not necessarily vice versa.